This video is about the conservation of momentum in 2 dimensions. So it's one step further than the last lesson, conservation of momentum in 1 dimension. I'll point out that the equation will be the same for the most part. Whatever momentum you had before a collision should be equal to whatever momentum you have after the collision. You shouldn't lose any momentum. It's just going to redistribute amongst all the different parts. So that's going to hold true. The only difference is now we have to break up our momentum in terms of its component parts. So you have to separate the X and Y components, which probably means you're going to be doing a bit more Pythagorean Theorem, SOHCAHTOA, if you will, and separating of your individual momentum into X values and Y values. Same thing with your velocities. You'll probably want to separate your velocities into X velocities and Y velocities before you proceed. So just like the last video, I'd recommend you go to the PhET website. So if you just quickly Google collision lab and PhET, spelt P-H-E-T, it should take you to this little site right here, PhET. This is the one that I showed you last time. But if you click on the advanced tab, it will probably look like this when you first get on there. If you click more data, you can see more things. But you can see that it's 2 dimensions now. So 2 dimension is ticked off. And you can set your velocities however you want. I'm just going to leave these guys like that to give you a rough idea. It tells you what your masses are again. It tells you where they are within the X, which is horizontal, and Y, which is vertical. And you can associate the velocities to be whatever you want them to be just by clicking and dragging, or you can actually enter in the numbers. Make it 1 in the X, 1 in the Y, sorry, -1 if I want it to go down as a 45-degree angle. But I'm going to put it like that, I think. So when these two collide, they're going to redistribute their overall momentum. You can see here they've got the momentum separated into components of X and Y. Overall momentum, you'd have to click on show values and you can see it right underneath each of them. So the magnitude overall momentum of the first one will be 0.41 kilogram meters per second. The second guy has a much larger momentum because it has a similar velocity, but again, this guy has about 3 times the mass, number 2, than number 1. So its momentum is quite a bit larger. I'll just remove those values and we'll press play. They collide. You can see 1 was going off very fast. They have both had a slight direction change. 2, not so much, but it did slow down. It transferred a lot of its momentum to number 1. If I show the values, you can see that in this case, their momentum is almost equal at this point. But this red one has sped up quite a bit. And you can look at their individual components if you would like. This is handy because you can just get a general idea to something realistic and practical when you're trying to do some of your problems. It might be a little bit hard to make it exactly like your problems with the masses and the velocities, just because it's set up in this X and Y format, so it requires a bit of math ahead of time just to break up the velocities properly. You can add more masses and let this thing go and everything will go nuts. You'd end up looking like a pool game where all the spheres are just going at random for the most part until they have collisions. And you can see how every time there's a collision, momentum is changed. So number 2 almost lost all of its momentum, so it was small enough that they couldn't actually have the arrow on there. So you can play with that. I'm going to move on with the lesson because I don't want this video to be too long. So moving on from that, here's just a stationary example. If you have 2 masses, kind of highlighting what I just did in the animation. This one's going down into the right, this one's going down to the left, so you'd have to consider both of them in the X and the Y beforehand. So in the X, you can describe the orange ball as mass 1, velocity 1, cos of whatever that angle is to describe its X value. So what would it be like traveling in the horizontal only in that direction? So that would be this right here. Likewise in the Y, to describe mass 1 in the Y, you'd have to just take mass 1, whatever the velocity 1 is, multiply by sine of that angle to get the, to get that vertical component. So mass 2 is going left, so therefore left would be considered negative, but it's also going down knowing that down and right are positive, we would just write it down as such. They have a bit of a collision, they redistribute their velocities, and this is just an example of what it might look like afterwards. Afterwards in the animation, both my masses were going down and to the left, but that was just due to the values that were assigned to them. So we'd have to separate them out and make your x's. So this is the x direction right here, and this is the y direction right here. So you'd have to break up your conservation momentum in both x and y. Likewise, in a lot of these conservation of momentum problems, you'll be looking at things that might explode or detonate. When that's the case, you have to recognize that there might be no momentum initially. So in the case of this Acme little explosion, this bomb is at rest ahead of time, and since it's at rest ahead of time, it has zero velocity, and therefore its initial momentum is also zero. It goes kablooey, and of course a bomb will go up in only 7 different fragments, or at least that's how this one's written down. Obviously, this is a real detonation. There'd probably be thousands, if not millions, of little fragments here, there, and everywhere going off in all sorts of different directions, but leave that to simulations and supercomputers to actually figure it out properly. Just for visual sake, this thing had, its mass got divided up into 7 random fragments. They're not all in equal mass, and they're all going off in different directions. So I just number them randomly 1 to 7 as we go across. And if I copy and paste each of those individual vector lines, individual momentum, they would connect. You can read this if you want. They would all connect and form a closed loop. When you form a closed loop, there is 0 resultant vector. And when there's 0 resultant vector, that means there's no final momentum. All these individual momentum vectors cancel out in the end. So you're back to 0. So that's how your conservation momentum will work if there is no momentum beforehand and suddenly it seems like there's momentum afterwards. You just have to look at all the individual parts and add them all together. So I'm going to do one problem with you guys on this video because it will take a long time. I think this is on page 56 in your notes, question 33. So it's a bit of an easier problem just for presentation purpose here. We have an 8 kilogram shell that's initially moving at 28.8 meters per second east and explodes in 3 fragments. 3 kilogram fragment flies north at 50 meters per second. A 2 kilogram fragment flies directly east at 40 meters per second. Calculate the velocity of the 3rd fragment. So it didn't give us the mass for this 3rd fragment, but you can easily figure that out just by taking 8 minus 3 minus 2, and you should just be left with mass 3 is equal to 3 kilograms. We'll come back to that later, but just right off the bat, even though that's not given, you can quickly figure that out through quick subtraction. So that's our question we're going to do. I drew a little picture that goes along with it because this is kind of what I see when I think of this problem. So I've got some random artillery shell or bullet. So there's bullet bill. It's traveling to the east, so to the right. It's going to suddenly explode, and we know 2 fragments for sure, the fragment going north and the fragment going east. Those 2 I know, so I made them little red vectors and solid. I don't know where the 3rd fragment's going to go, but I do know that the momentum beforehand has to equal to the total of momentum afterwards. So beforehand, I'm going to the right. 1 fragment that I know for sure is still going to the right. Another fragment is going up. So since this guy had no vertical direction ahead of time, nothing was going north, nothing was going south, suddenly after the explosion, a piece is going north. I have to have something going south. All right, so something has to be going south. Therefore, I can eliminate this guy. This guy is not possible because in order for something to be going north, I have to have something going south, and this guy wasn't going south to begin with, so, or north, so I have to balance out my vertical. So that's kind of a dead giveaway. I know it's not going to be this guy. Otherwise, it could be any one of these ones because we still have rightward motion, we have upward motion, so up has to be canceled off by down, and right could be canceled off by left, depending on how, well, we're still going to have something moving to the right afterwards, but this is possible because it could just be a light fragment, small piece going, or really slow going to the left. It's not a small piece, it's 3 kilograms. It just could be going really slow to the left. So we don't know, we have to do the math. So if I make right and up positive, so that's east and north, are going to be positive, and just figure out what I know ahead of time. I know it's an 8-kilogram artillery shell. It's going almost 30 meters per second. So roughly highway speeds. Do the quick math. You'll get roughly 230 kilogram meters per second. It's a rounded number just for on here. I think it's 230.4 kilogram meters per second. I'm just going to stick 230 for now, and I'll assign my direction. It's going east. So that's what I know ahead of time. If I break it down into component forms, I could just call it 230 kilogram meters per second in the I direction and 0 in the J. Or the J representing the north and the south, because there is no north and south to begin with. And then I will look at all the fragments. So the first fragment, so that's going to be momentum 1 prime, so that's after the explosion, is broken down to its individual mass and its velocity prime. So I know it's 3 kilograms at 50 meters per second north, and you can just do that quick math, and you should end up with this. It's going directly north, so that's 0 in the X, 150 in the Y. If by chance, I'll just use this little pencil here, it wasn't going directly north, maybe it was going north and east, I would have to break this thing down into components of right and up, so east and north. So in that case, I'd have to, if I just take my Y direction as an example, I'll just call this momentum randomly P. I would have to get P in my momentum and my Y would have to be whatever my hypotenuse is. So in this case, it would be 3 times 50. So I guess I could just say 150 and then multiply by sine of whatever that angle is. Oops, mouse drawing. Sine of whatever that angle is, and that will give me my Y component. Likewise, I'd have to do your X component. I just described how to solve for Y. For my X, I would just take my hypotenuse, multiply by cos angle theta. But this problem is a little bit easier because it is going directly north, so I can just ignore that for this purpose. Scrolling down, my second fragment, I know is going directly to the right. I know its mass is 2 kilograms. I know its velocity is 40 meters per second. So you can just do that quick math, get 80 kilogram meters per second. And if I write it down in component forms, I can just call it 80 kilogram meters per second in the I direction, which means to the right, and 0 on the Y. And then we have the issue of not knowing the third piece, but I will set it up. I don't know what the third velocity is, so therefore I can't actually calculate the third momentum. I don't know its direction, so I really know nothing. I'm going in the X and the Y. I still need to figure that stuff out. So I think I skipped a slide. Oh, no, I must have deleted it. So if I move that off to the side, I'll just, questions over there. This is my beforehand. This is my afterwards. I've got my third momentum in the X that I'm not aware of. I've got my third momentum in the Y afterwards that I'm not aware of. And those are what I need to find in order to continue. So I like to separate things into X and Y direction, and then you have to pick which one you'd like to work with first. Don't do them simultaneously, just pick one. I'm going to pick the Y direction first because if I look at my initial momentum, I was traveling 230 kilogram meters per second to the east, so that means I have no north-south direction. So I would rather work with the Y direction because that's one fewer variable. So let's start with Y first and go from there. So I know that up is going to be positive, so that's going to be north. And my equation, I didn't draw the vector symbols in, but I know that my total momentum in the Y direction beforehand must be equal to my total momentum in the Y direction afterwards. So rewrite the equation. I only have one beforehand, so there's only one mass, therefore it's only possible to have one momentum, so therefore there's just one variable on the left, that's before. And I have 3 fragments afterwards, so I'm going to put all 3 fragments there afterwards. I figured out the numbers I need to figure out for afterwards, so momentum 1 in the Y is going to be 150, momentum 2 in the Y is 0, and momentum 3 in the Y, that's what I'm trying to find. So plug in my numbers, 0 initially for the Y. It looks like this. So as you can see, 0 there, 0 there. The only way to cancel out the 150 kilogram meters per second is if this is a negative 150 kilogram meters per second. So if you bring this to the left, it would be negative, and you would end up with the momentum in the third fragment should be a total of 150 up on the vector arrow there. There should be vector arrows all the way down. It's just I got lazy. So we should have 150 kilogram meters per second acting vertically. Negative means it's going south. So that's something we'll talk about in a moment. Next, you can go to your X. So you set it up pretty much the same way. You define, I'm going to define keep right positive because it was going east initially. The total momentum beforehand must be equal to the total momentum afterwards. So I only have one momentum beforehand. It's 230 kilogram meters per second acting towards the east. You have three fragments, X1, X2, X3. We've already solved those, so that will make this a little bit easier. You can do this all simultaneously. It's just a bit messier. So since we solved all those numbers beforehand, I just put them in here, 230 from the initial, 0 as my first fragment because it's going north only. Second fragment was only traveling east, so that's where that came from, if you forgot. And again, I don't know my third fragment, so the only way to get px3 all afterwards all by itself is to bring the 80 over the other side. 230 minus 80 should give you a positive 150. I'll add the vector arrow there because, again, I was lazy. So I've got the vector for my third momentum traveling to the X. I've got the vector for my third momentum fragment traveling in the Y. So positive means this one's going east. Negative means this one's going south. So I've got an east direction, I've got a south direction. Now we just draw in our vector arrow. So typically it's best to just draw these things out. I know I didn't draw this to scale, I just kind of eyeballed it. So momentum of the third fragment afterwards going to the right, momentum of the third fragment afterwards going down. I've got next, I've got a Y. Finish your triangle off. You're looking for the hypotenuse of my third fragment afterwards. So that's just Pythagorean Theorem. So if I shrink those down so there's more room on the page, we're going to solve for that triangle at that point. So Pythagorean Theorem says c squared is equal to a squared plus b squared, or my hypotenuse of my third fragment momentum is equal to its x component squared plus its y component squared, all in the square root. And if you plug in, so we said this was 150 squared, added to another negative 150 squared, negative will cancel itself out. Add them together, take the square root, you should get 212 approximately kilogram meters per second. So I didn't type those in, I just figure at this point in the semester you guys can do that kind of a math. So that will just give you the magnitude of my third momentum fragment. From there, you kind of need to know the angle. Now, in this case, you should probably recognize that if you have an equal X and Y values, that this guy's going to be 45-degree angle. But just as a general reminder, because you're not always going to have a nice 45-degree angle, I would take the inverse tan function of my opposite side divided by my adjacent side, mainly because I typically draw my vector arrow, my vector triangles, X first, then Y. So because I always draw mine X first, then Y, it's always going to be, in my case, my Y value divided by my X value. If you decide to draw the Y value first, then the X, you'll have to flip those around. So do that real quick. You'll see that it should give you 45 degrees. I know I've used some rounded numbers. I don't believe this is exactly 230. I don't believe one of these was exactly 150. I think this one's slightly different in the X. So it might be something like 44 or 46, but it's really close to 45. So this is just a rounded number. Next step from there, recognize this is a vector, so write it in proper vector notation form. So this is from the east axis traveling 45 degrees towards the south. And of course I typed in north because somehow I missed that. Well, I'll just fix that now. Mistakes happen. All right. Don't know how I didn't catch that. So it's going south. Recognize it's going east 45 degrees to the south. Try to watch the typos. Now, the question asked for, you probably can't see the question anymore at this point because I kind of made it really small just to fit everything in. It did ask you to calculate the velocity of the third fragment. We did not do that. We calculated the velocity of the, we calculated the momentum of the third fragment. So we did not calculate the velocity, we calculated the momentum. But the last step is pretty easy. We know, so if you look over here where the mouse is, our our third momentum fragment is equal to mass 3 times velocity 3. We know the mass is 3 kilograms, so it's just a quick manipulation of this equation. And so from that, we have our final velocity of the third fragment is equal to the momentum of the third fragment divided by the mass of the third fragment. So really, this part's just a nice quick little, take your last answer divided by 3 kilograms, the masses cancel off, and you should be left with, and again, aside from the typos, because I don't know what happened while I was typing this up, must have fallen asleep. It's too late to re-record. That'd be a lot of extra work. So that last little bit, you would just take your final momentum divided by the mass. This will not affect the actual direction. Don't take the direction and divide it by mass. You can't do that. You just take the momentum divided by the mass. So you could have divided up here when you found the magnitude of your hypotenuse, you could have divided by 3 kilograms at that point, but that would have just given you the speed. You would have said the answer was 70.7 meters per second. You wouldn't have had the actual angle, but you could have just done that separately off to the side. So really it doesn't matter what order you do that last couple steps in, as long as you remember to represent it as vector notation when you're done. Now that was a lot of work. These problems do take a little bit of effort. They take a little bit of extra time to do because there is a lot of steps in between. And I see I left one of my typos in there still. So that was going south. Again, very sorry. So they do take a little bit of effort. It's really easy, as you can see, to make a little mistake here or there along the way. So always try to make sure that you remember what directions you made positive, therefore what directions are negative, and try to just keep your stuff organized as possible. If you want, I believe the questions start on page 56 for two-dimension momentum. They're a little bit challenging. So if you are up to the challenge, give a few of them a try. And I'm going to stop the video here before I make further mistakes.